Oh, I guess. Welcome to this week's Graphics Programming Weekly. We're going to be covering the Chapter 3, Part 2 of the VK Guide. In it, we set up OBJ model loading, we get the depth buffer going, and we reorganize the project to have a scene management system. So because we rendered a triangle last week, actually I fixed it up so it renders. So let's actually see it rendering. We got a triangle going, but we got it going using a buffer of vertices, meaning we can put arbitrary numbers of triangles in. Now we're gonna hook that up to a model format known as OBJ so that we can save the models on disk and load them with ease rather than defining them in code, which is what we're currently doing somewhere in the code. Okay. The OBJ format is very simple. It's a text file. It contains vertices, normals, colors, texture coordinates in separate lists, and then a list of faces that hook them all up. Where is assets? Monkey, yeah, okay. The format looks like this. It's very simple. We have an object called Suzanne, and this is our list of vertices, V for vertice, and we have our giant list. You can see that there's a lot of them. VT stands for texture coordinate, so VT, so this would be coordinates that correspond to the texture. We go further down, we have normal, and then if we go even further down, there should be faces. So this is saying there's a face with triangles with vertex 4711, 321. Are they reusing? I don't actually. Some of these things I forget how they work, but
I think it's the point and then the normal and then or text coord normal. I think that's what the slashes are.
Oh yeah, so you could reuse colors and other things if you wanted, it sounds like. But even though this is a very simple format, we're not going to be bothered with writing our own parser and understander of it. We're going to use the Tinyobj loader, which is already in the project in the external folder, so we don't have to do anything to get it. We'll start by just creating a mesh in the the engine class. We'll want to add a new function to the mesh code. So here we have load from OBJ. So this will load an OBJ and write the data into the vertex and this. And we need to edit the mesh file to include it. So this function will just copy paste the outline of. The format is very simple, but the way it's stored in text is not how we store it on the computer, nor is it how it's handled abstractly. So after we've loaded the file, we're going to have to parse it and pull apart what we need and put it into a format we can parse. To load it, we need to define a couple of variables to store the data. So a OBJ file can contain multiple shapes. That was why we need a vector of shapes. Tinyobj provides a struct that stores the information for it. You can also have multiple materials. We're not really using that yet. And the vertex attrib is the data inside the file rather than the description of it. I'm not quite sure. So this is a lot of this code is stuff that you copy paste from places. You understand how it works, and then you forget the first time you look away from it. So to load the actual thing, we have Loadobj. It's a function in the Tinyobj library. We've included Tinyobj up here. We pass in the attrib shapes and materials vectors. So you can see it takes pointers to it. So actually, Oh, okay, yeah, this is not a vector. So it takes pointers to the vectors that we need. And then we pass in the file name. We have our warn and error as arguments so we can get errors out of it. We check that there aren't any warnings. If there are, we print them. If there are errors, we also print those, but then we return false because if there's an error, we can't load the model and we want to report that we can't load the model. This is the big function that goes through and pulls apart the code and turns it into an actual vertex. So we will loop over every shape in the file, and for every face, we're going to go over each of the corners of the face, i.e. the corners of the triangle, and get the index of that vertex. We're going to get the X, Y, and Z as well as the normals. We could also, this would also be where you get the texture coordinates. And we see attrib vertices, it just is a, if we actually look at the definition, this might illuminate it. Okay, no. It's just a vector of floats. So real T is a typed F for float. So vertices is a giant vector. It's not delineated in any way. Same thing with vertex weight, normal coordinates, all of these things. So don't need that. When we're parsing it, we need to access the correct place in it. So vertex index is going to be calculated. Yeah, I'm trying to explain this function, and this function actually takes up quite a bit to explain. Just understand that we're processing the mesh, and it's stored in separate vertex position, vertex normal, texture coordinate arrays, and we're having to pull it all together into a single array or a single vector that contains all of these disparate points. So we have the Vx, Vy, Vz, Nx, all that. We have a vertex struct. We assign all the things we need, and set the color. Though right now we're just using the normal, and then we push back the vertex onto the vector of vertices, and then we iterate as far as that once. Note that OBJ files can contain more than triangles. They can contain faces with 4, 5, 6 corners, but we assume it only has 3, and you really don't want to deal with meshes that don't have triangles. You'll have to turn them into triangles anyway, because that's what the hardware accepts, but so it's just easier to just not handle it or require a pre-processing step. So that's the function in way more detail than was necessary. To use the function, just call the function, and we go back to here. I believe this function's the very end. Where's the load meshes? Here it is. Yeah. So we can load the monkey, and then we can upload the monkey to the GPU. So now this mesh is uploaded and ready to be drawn with. Since we're going to be drawing a buffer of variable size, we need to use the size of the vertex array when we're drawing it. I think the draw is up here. Let's forget. Yeah, it's over here. Here we have that. So we're going to be drawing the triangle, and then we're going to be drawing the monkey, and we should get this rather odd-looking feller if it builds. Why didn't it build? What did I fail? Offset. Oh. Well, then I delete that, save, and try again. Woo! Okay, so we can see the triangle. We can also see the monkey. This is Suzanne. She's the mascot of the Blender 3D modeling program. You can tell that there's something quite wrong with it. It doesn't look like a solid monkey. It looks like a very weird looking cloud of triangles. What's happening is the GPU is being told, here's a list of triangles, draw them, and it's dutifully drawing them. What it's not doing is using any sort of depth testing to make sure that the triangles that are in front of other triangles get drawn and triangles behind other triangles don't get drawn. So the GPU is like, okay, I'm going to draw all these triangles, and it does in whatever order it wants to because there is no defined order. To fix this, we're going to have to add a depth buffer. The classic way of sorting the classic way of drawing triangles so that there's no depth issues is using the painterly algorithm, where you draw the farthest objects first, and then you draw near objects until you draw the closest objects last. That way, the things in front don't occlude the things in back because you've drawn them last. This doesn't really work in practice because you have to sort all the triangles, and it's really quite complicated because it doesn't solve the case where you have overlapping triangles. And the solution that was at the time of its inception a bit more performance intensive, but once they added hardware to handle it, it became the best solution, was to do per pixel storing of the most recently rendered depth value. So you'll have a buffer that contains not the color, but the depth value, meaning a floating point value of how far the triangle is in the scene. This way you can quickly check, oh, I'm drawing this triangle that is behind the last rendered triangle in the scene. Not last rendered at that pixel's point. If it's behind it, you can discard it. But if it's in front of it, you go, oh, okay, well, I'm in front of it, so I'll draw it, and then I'll update the depth buffer to be newer. Doing that requires creating a texture, which is what we'll do in the next chapter. To create a depth image, we need to allocate memory for it. Because we have to allocate memory for it, it's not a part of the swap chain. It's not something that gets sent to the monitor. So we have to manage it. Thankfully, VMA will actually do all the memory management of it. We just need to set up the creation and various information to set up about it. In Vulkan types, which I'm failing to find, is it just up here? Yes, I think I need to add it. So we have our allocated buffer. We're going to do the same thing with image, BK image plus its allocation that comes from. We're going to add the depth texture and the allocated image. Now, the allocated image is what stores it. The image view is how we get access to it. We need to create the image, and we'll put its contents into here and here. But we'll also need to create an image view, which is the way we can access it. And it's very useful because there's a lot of ways images are used that aren't just a pointer to its data, like a buffer would be. So we have our initializers, and again, I think I need to. Oh, it's over here. That's where it is. Yeah, here it is. So we're gonna add 2 new functions to it.
Hey, I'm sorry to interrupt. Where can I grab this source code from?
You can grab it from their GitHub, which is here. Specifically, all chapters. So it's not in the main GitHub page. It's in a branch, all chapters, which is weird, but it does mean that the master this is where all the web dev stuff goes, and then all chapters is where all the code goes.
Gotcha.
Yeah,
Cool, thank you.
no problem. So oh, there it is. Okay, so image create info. we fill out the struct, normal S type pnext stuff. The image type, there's a whole bunch of parameters in here we need to set. Some of them we care about, some of them we can set a value and be done with for what we're doing. Image type is the different types of image. There's 1D, 2D, 3D, and is there cube maps here? Let's find out. No, just 1, 2, and 3D. So that's it. So the format is the format of the image. This will be the layout of the contents of the pixel. So the RGB channels, whether it has an RGB, RG and B channel, what the size of those channels are, 16, 32, 24-bit. Extent is the actual size of the image. This is a VK extent 3D that has height, width, and depth, as we can see here. If you're making a 2D image, the depth doesn't matter, but it's whatever. MIP levels is the number of MIP levels to generate for the, to allocate for the image. We're only going to handle one currently. MIP levels are very useful. MIP mapping is very useful, but adds additional complexity. Array layers, you can have an image of multiple layers, including a cube map, not cube map. Well, I guess it is a cube image, but not a cube map. So you can have an image that contains 3D images in arrays. We're only going to have one. Samples is for multi-sampling. Depth buffers and render targets are where you'd apply multi-sampling, but we're only going to use 1 bit because we're not going to use multi-sampling in this tutorial. And lastly, not lastly, tiling. This is probably the most important parameter here that's not easy to explain. Yes, you can have someone ask if you can have cube map arrays. Yes, you can, but a cube map is really an array of 2D images, if that makes sense. It's really weird. Where is it? 3D images. I forget. You have to look it up. I'd have to look it up. So the tiling of an image specifies the layout the image has on GPU memory. So the naive way to lay out memory is linear, and that's the other option for tiling here. Linear means, actually there's a weird one here, but linear means that the rows are row by row, and then it's then column by column, where everything is laid out in a 2D grid in memory. It's actually quite slow to access local data using this layout, because if you have a caching scheme where you load nearby data when you access an individual address, pixels that are nearby will only be horizontal in the image. Any pixels vertical of the one you're trying to access are not going to be in the cache because they are stored non-contiguously with your data. The solution tends to be proprietary, but they almost always follow something like a Z-order curve, where they use fractal-like patterns to lay out the memory so that contiguous access of pixels is coherent in the caches. So this would be the order that the pixels are stored in memory. So if I was trying to access this pixel, getting the pixels to the left, right, and south are only a handful of steps away, versus in a linear access where it might be one row down or a row up, which is very slow. So if you're allocating memory on the GPU and it's going to be used for rendering either to or from, it's very important to have it in optimal. The only time and there's a lot of restrictions on things that are not in optimal format. So it behooves you to use optimal where it is appropriate and linear where it is appropriate. The times you want to use linear is if you're copying data to the CPU to either write to a file, to process for something else. It's because optimal is a tiling that is really a optimization for the GPU manufacturer to put the data in the format it thinks is best. You can transfer between optimal and linear, but it incurs a cost. Like it effectively has to copy the data around to transform it, and you want to do it as little as possible. So tiling, there's more to talk about, but we'll continue going on. So the usage flags describe the things that you'll use the image for. If we go look at some of the example ones, if it goes to the right place, if it here, there's quite a few usages. So we have transfer, sample, storage, color attachment, and depth stencil attachment. We've used color attachment. This time we're going to be using depth stencil, and because we're in a initialization function, we've passed it in as a parameter. But as you'll see in a second, we're going to use the depth stencil usage form because they're flags, so you can combine them. So if you had a depth stencil that you wanted to copy to, you could combine it with the copy source or the transfer source. And yeah, that's an explanation of all those parameters. So now we get to the image view. You can think of a VK image as a allocation description, like a description of a chunk of memory, and that's useful if you could, that's useful on its own, but it's not necessary for good abstraction because there's a lot of times you are not wanting to access the entire allocation. You may want to access parts of the allocation. This is where the image view comes in. It is effectively a pointer to the allocation. You pass in the format, the image, and the image aspect flags, which is similar to the usage flags. We can actually look at what they contain. You can see that color bit, depth bit, stencil bit, and there's some stuff for various DRM and other things. So we have a view type. We're going to be doing 2D images for the most part. So you can just hard code it to 2D. There's 3D and 1D, just like the image type here. It's image view type because it wants to be special. No, this is what makes image views interesting. You can specify the MIP level you start at and the number of MIPs. This way, if you wanted to render into an individual MIP map level or sample from, but you didn't want to create a new image for it, you could totally do that. Same thing with the array. This allows you to easily redirect where you're writing your data to or reading your data from. Needs the format and the image which we pass in, and then we have our info. So to actually use this, we're going to go to our swap chain creation. We're only going to need one depth buffer, I believe, because it's cleared at the start of a frame and written to during the frame, but by the end of the frame, we can throw it out, or at least we can forget about the contents of it because we're not going to present it to the user. Where's the swap chain initialization? Here. Okay. So we create our swap chain images by getting them from the API, which we use the VKB wrapper function to do that for us. Because the depth buffer isn't a part of the swap chain, we have to create it ourselves. So we're going to start copying code. We got our image extent. It's going to be the same as our swap chain image size, width and height. We're going to hard code the depth format to D32. That's a well-supported format. It's not the best format. I have found that the performance guides definitely recommend specific formats based off the hardware. And it also depends on whether you need the stencil bits. So this is something that I think if you wanted to publish a game, you'd want to reassess. It's like 5 lines of code, but I want to mention it. We get our image create info. We pass in our depth format, which we set up above, and we're storing it because we're going to need it later. We have our usage of depth stencil attachment, and we have our size. Once we have that, we can create our image using VMA. Because this image is going to stay on the GPU, we're not going to copy it to the CPU at all. We're going to use the GPU only format, which means device local. And we want to make sure it's device local. I'm going to call the function to create the image, passing in all the necessary parameters, the image and the allocation. Now we're going to create the image view. Use the format again. We're going to take the image we've just created, and we're going to use the depth bit. And I thought there'd be a size, but apparently there isn't a size we pass in because the size is constant. Yeah, okay, so the image view doesn't contain the size, like the extent in pixels of the individual images in the layers, but you can change the layers and MIP levels you're rendering to. Okay, I forgot about that. And then we got to add it to our deleter because we're delete at the end of the frame or at the end of the game. Destroy the image view and destroy the image. So here we get to the fun bit where we have to modify our render pass. We now want to render stuff to both a color image, the one that goes to the monitor, and a depth image, the one that stores the depth values as we render. So we're going to add a new attachment. So we have attachment description here. And it's going to be our depth one. Notice it's more or less the same as before with only a few differences. Our format is changed. It's no longer the swap train image format. It's the depth format. And our final layout is going to be depth stencil attachment optimal rather than layout present source KHR. So it's saying it needs to be optimal for depth stencil work. Note on the load, we want to clear it, same as before. And because it's a depth stencil, we actually care what this is. But we're not doing anything with it other than clearing it, which here we see that we don't do anything, but it wouldn't apply anyway. So here we clear our image before we use it, and then we throw out the results afterwards because we don't care. I guess this could be don't care. Maybe, I'm not sure. Don't quote me. Look it up. Read the spec. Some of these things I have not a perfect memory of. So we need to add a new attachment reference. This one refers to this where image. It'll have the depth stencil attachment optimal as the layout. It's just remarking what those things are. So we have our subpass description. We're going to add a depth stencil attachment to our subpass description. Note that it's P depth stencil attachment, not attachments, because there is only one slot for a depth image. You can't render to 2 depth images at the same time. It's not something the hardware or the API exposes. Because it's more the API. The hardware could do whatever, and it's whatever the API defines that matters. We just need to change our attachment count and create an array to store them and index them. So here we're taking the address of the first attachment. And so that's how we're passing it, because we want a pointer to an array of attachment descriptions. And so here we're just copying them. We're not, we could make them in situ, but this is the optimizer will make good work of that. So like a handful of things left to do. we have updated our render pass, which describes the attachments that are going to be used in our rendering. Now we need to update our frame buffers to include describing those things. So we now have 2 image views, not just one we are going to use. Whatever the image view we're going to use, and then the depth image view in the second one. So this should be just attachments, yes, because it's a vector. We're not indexing each swap chain image directly, or image view directly, because it's a pointer to them, and there should be 2. Why? Where did the count get set? Was I doing it wrong before? I don't see where I set that. Spooky. So I think that's everything there. So we've updated the render pass. We've set the image view handle in the frame buffer. Now we need to update our pipeline. So we're going to add another initializer to our list of initializers, but this time we're actually going to really implement one we had before. We just didn't define, right? Is this not supposed to have that on there? No, it is. It's wrong. Does it not have one? It doesn't. Okay, we didn't create this before. So I guess we get to copy this definition over. Okay, I was wrong. Which has been known to happen many a times. Okay, so our pipeline describes the fixed function state. The depth testing is a part of that fixed function state. Therefore, we need to update our depth testing in the pipeline when we create it. This struct defines whether the testing is on, whether we're writing the test on, and the comparison operation, whether we're these are we're setting. These would be useful if you're doing shadow mapping, if I recall correctly. These kinds of max min bounds stuff. It's also useful if you're just only wanting to render a subset of the entire scene. Usually, the usual range for depth values is from 0 to 1. This actually sometimes is useful to be 1 to 0 because of reverse depth buffers. Really cool stuff, but a bit out of scope. So if you look at this and you go depth test enable and depth write enable, and you assume that enabling testing and enabling writing of the testing are always going to be true, why are there 2 separate things? Well, sometimes it's useful to know if you've passed or failed a depth test, but you don't want to update the value in the buffer. Say, for instance, a special effect that goes, well, I only want to render if I'm visible to the camera, where the test would pass, but I don't want to update it because that would cause other things to go out of whack. Oh yeah, rendering transparent stuff. Someone Jager comments. That's a great use case where you don't want to write, but you do want to test. So we'll add the struct to our pipeline builder. We'll just slap it here. And where do we call the function? Oh, we call the function here. Oh, in the build pipeline. Can you tell that I'm also reading the code as I'm drawing it? Yes. Put down here for a reason, didn't I? Let's build pipelines, right? Yeah, that isn't it, pipelines. I'm sorry. I'm trying to find the function so I can F12 it. There. Oh, it was right below it. I'm silly. Okay. We need to update our, yeah, here, depth stencil. We've added the thing. Now we want to assign it since we're going to have it. And we'll use the same depth testing for all of our pipelines, which means we don't have to set it per pipeline. We can just set it once and then call it good. Vertex input, all of these things. I'll put it here. We'll test, we'll write, and we'll use less than or equal. One common mistake I see beginners make is when their depth test is the wrong one or slightly off. So always a good idea to check what's happening and know it. And finally, we just need to update the clear color. So we have our depth texture, we're reading from it, and we're clearing it, but we haven't said what value to clear it to because Vulkan is explicit and does not assume that it has a clear value of 0 or 1 or 10 or whatever. We have to set that manually. We'll do that when we begin the render pass. So now we'll change our clear count values from 1 to 2 and change our array to that. Ooh, okay. Does that work? It's yelling at me. Why is it yelling at me? Did I copy wrong? I don't know. Yes, it's, what is the error? Okay. Oh, values. There we go. That was a typo. Okay. Oh boy. And it crashes immediately. I bet you that it's something stupid I did or didn't do. And I don't want to debug it. What did it? That's valid. Okay, I'm gonna let this rest and move on to the last bit of this chapter, which is scene management. I'm not gonna implement it because it will take more time and a lot of it is just copying code around. We're going to introduce the material struct. The material struct currently just contains a pipeline and pipeline layout. And then we'll add a render object struct. A render object is a pointer to a mesh, a pointer to material, and a matrix. So we want to refactor the scene management to be a separate list of materials, meshes, and then a list of render objects. That way, when we render it, we're not rendering each object individually. We're not conceptually doing that. We're conceptually iterating over an array of render objects that are spread across the materials. The reason we want to do that, the reason we have a material struct is that we want to sort by material. Generally, binding pipelines is rather expensive, so we want to minimize the amount of pipeline binding we do. So what we'll do is we'll have a for loop, if we can find it, that just goes over the entire okay. Yeah, the entire list of objects we're wanting to draw. Oh, okay. I thought this sorted. Oh, I misread. So it just goes through the list of render objects, and it will bind the pipeline if it has changed. Generally, we want to sort it so that there's a for loop by the pipeline and then an inner for loop that's by the object. And then per object will bind the, not bind, will set the model matrix for that object, using whatever method you have. So we're going to use push constants for now. And then we'll render the object using those things and go onto the next object. If it's using the same vertex buffer, we'll just keep the same vertex buffer, change the push constant mat4, render again, and just go through the entire scene like this. The implementation detail that is necessary to explain is the unordered map here. So we're storing a map of the materials and meshes. We could use a vector, but a very nice property of an ordered map is the stability of the values. Oh, it does? Okay, someone comments, sorting is an exercise for the reader. Yeah, I must have read that and thought that's what it did because I was skimming a bit too quickly. Okay, so we have an unordered map and it's keyed off a string and it stores the material meshes. This way, a render object itself is just a vector of structs containing a pointer to a mesh and pointer to the material. We can store the pointer directly and we don't have to update and index every time we change the, if this were a vector, we'd have to constantly update these pointers here and that would be a mess. We have some helper functions, create material, and get mesh. So we search by string and we return the pointer to it. This is literally just it forwards to the find function on the unordered map. It's very simple. And if it isn't, it just returns. If it finds it, it just returns the object or it's a pointer to the object. It's the mesh or material. You can see that these are literally copy pastes of each other with the name changed. We'll assign the name monkey to the monkey mesh as well as triangle mesh here. That way, if we want to get the monkey or triangle mesh, we don't have to have the object, like the variable name. We can just search for it by string. Gets it off. This will allow future expansion in nice directions. And most of this is really just reorganizing the code we already have. See, we have here our initialization. The example scene, which is not shown here, is it shown here? Is it shown here? Yes, I believe this is the it creates 20 triangle objects. So the render object will have the triangle mesh and the material and the default mesh material, and it will create them on a grid 20 by 20, and its output will look something like this. We set the scene, the scale and translation just based off the position and just a scaling down. And we add the renderable. The tutorial comments that this is a relatively naive but performant render loop. That's because it has the optimization that it does not rebind the pipeline if it doesn't need to, nor does it rebind the mesh, the vertex buffer. You're not going to be rendering AAA games with it, but you can definitely do a lot, and it is a good base to go from. I would suggest implementing the sorting by pipeline, as well as refactoring out the push constants for map4s, but that's what this next chapter does. So we'll continue that on there. It doesn't have index buffers yet, but that's it's similar to Vertex buffers, just a bit more. And there's actually several good tutorials on how to do that already that you can find. You can render AA games with it. Yeah, actually, you could get quite far with this as it is, just with some feature additions where you need them. I'm curious about trying to fix this in the couple of minutes I have left. If any of you can spot the bug before I do, did I never create the allocator? I don't think I did. Okay, so I think what happened is I'm trying to use VMA's allocator and I'm initializing it. Where is it? Here, but I'm using it here. So what I'm going to do is move it up here, save, hit F5, and it works. Okay. So here's the depth buffer. And there is no material files currently on file. So are there any questions? Are there any comments or criticisms?
It's beautiful.
Yeah, just keep it going. Yeah. Need to make sure to.
I would like to criticize the fact that I'm pretty sure that triangle is causing brain damage at the moment.
We can fix that. Where is that triangle? Here. No, it's in the drawing. We have our right here. We have camera position, view, model. I want to do GLM.
You'll probably apply the same model for both meshes.
It probably will, but we can some live code in here. So this is doing what this does, but in a very minified amount. So we have our thing here, mesh matrix. And we'll take the model and go GLM translate model GLM vec3 0 1.5f0. And does it compile? No, it doesn't compile. No, it doesn't compile. Why doesn't it compile?
You redefine mesh matrix.
I did. Thank you. Got to figure it out eventually. Oh, that's the opposite of what I was hoping for, but it's even nicer because now the monkey her head is resting on the triangle.
I feel much better for it now. Thank you.
You're welcome. I can actually do 1.5f and get it in front. So, or to the side, because I don't know my axis apparently. You can get to the front and to the side, but I think the front's fine. Okay. Oh, hello.
Oh,
Now I'm getting. Now we're giving the monkey brain damage directly by having her head go through it.
Some kind of endoscopy.
Does look cool. Fun fact: you can tell the normals based off the position because the color is like anything in the same relative position. Like it's weird. Like I don't know how to describe it. The normals are the color is based off the normal, which makes it look weird.
It's the global normal that you're using.
Well, it's
in world space.
no,
In
it's
object
no,
space.
it's model space.
object
Model
space.
what
Yeah,
I'm saying.
that's the word. Yeah. Okay. Well, I think that does
It's
it
on the
for.
normal.
Can you turn backface calling on? Is that easy to do?
Yes. It is in the one of these initializers. I'm pretty sure. Cold mode. Yeah, this one. Okay, because I don't remember the name off the top of my head, I will use IntelliSense and just F12 my way to victory, which here. So let's see. This should enable backface calling. It enabled front face calling, so we're getting the very
Oh.
creepy.
Because your model is counterclockwise.
Yeah.
Winding order. Yeah.
Is it counter? Is that the right name? Oh, okay. Now the triangle is going to be invisible, but at least the head is. Once it goes inside of us, it should work.
Nice.
It should disappear. Now it just the triangle has ears. Okay.
A lot better than inverted face.
Yes, I agree. Okay. Hopefully, by the time we get to the 4th chapter, I'll have implemented all this scene management stuff, as well as some of these fancy extra features like WASD and camera movement controls, and get some more fun meshes, so it's not just the default ones. But that's for next time. Thank you for watching.
Thank you.